right. Welcome, everyone. Thank you so much to attend this session. You're brave. It's just before the party. You are going to experience a little bit of Switzerland here on stage with the French accent and the German accent. So if you ever want to visit Switzerland, you are ready. This session is under the hood. So this is not directly technology you are going to maybe directly use. We are more about, it's more like computer science. We are going to show you how we did things, how we built stuff, how we went about solving certain problem. And it's quite different, right? So I'm going to talk about the arcade editor, how we built the arcade editor. It's a lot of abstract syntax tree and so on. And Stefan will go more like into 3D and WebGL and so on. So before I go really about the explanation how we build the arcade editor, just a quick reminder about what is arcade. Arcade is this expression language we created so that we can have a safe language that we can use across the different application we have, from pro to enterprise to online, etc. And for us, it's important to have a language that is, prevent injection, attack, and all this stuff. So basically, it's a language we created from the scratch. It was, and we will go in some details about this language in a minute. It can perform many things. It can be used in different aspects. So we use it behind pop-ups. We use it for labeling. We're using for the rendering system. We're using in dashboards to control styling of tiles in the dashboards, or even creating on-the-fly data sources for the dashboards and so on. So the arcade is used in many places in our system, and we have multiple runtime, if you want, of the arcade, because we have three different main systems. So here is the example where someone can author a web map using ArcGIS Pro, and this person create a nice pop-up, and in this pop-up, leverage arcade to tweak the pop-up or do certain things or calculate new data for the pop-up. When this is done inside ArcGIS Pro, the web map is saved. And of course, now that web map, if this web map is reused in ArcGIS Maps SDK for native apps, JavaScript, or dashboards, or even inside the map viewer, that same arcade expression can be executed in these different environments. So we have at least 3 runtimes, one for JavaScript, one for native application, and one in Pro. So that's one aspect of the arcade language. The next aspect, oh, sorry, I went, yeah, that's great. So where did we go? We had an arcade editor for a while, but this arcade editor was kind of basic. So people came with a lot of requirements. They said, it would be nice if we get better errors or warnings. It would be nice if you could make suggestions as I'm typing my arcade expressions. Like some of you are developers, so you know what means suggestion in Visual Studio Code or other systems. So that was a set of requirements we had. And also people asked for formatting. They said, sometimes those expressions are not well formatted. Can I format this? So this is a kind of an illustration of what I'm talking about here. So what we wanted is improve the arcade editor, provide a great way to understand what are the variables available for my expression, so what we call the global variables or the input variables. What are the functions that I can use for my expression, the different date function, feature function, geometry functions that I have available or not. And basically, I would like to have not only access to this, have a great editing experience where I'm receiving errors, warnings, suggestion, like I said, and formatting. So today, I'm not going to focus too much on how we build the right side of the arcade editor. That means exposing the functions and the input variables. It's more about the red boxes here, the validation, suggestion, and formatting. So that was the requirements. So how did we go about after that? We made a decision. So we studied multiple editor system that exists, coding editor system that exists out there. And you know what? We kind of like the VS Code a lot, so we said, why we don't reuse the same piece? And it's called Monaco, Microsoft Monaco. It's on the on NPM. It's semi-open source. So it's basically available there, so we decided to use that. It was very, we all like it, we like what it does. Monaco comes, when you install the package and everything, it comes with predefined languages inside. Of course, the TypeScript, JavaScript, CSS, JSON, HTML. That's pre-cooked inside the Monaco ecosystem. There is no arcade inside Monaco. So great, we selected an editor, we like it. How do we go about teaching Monaco about arcade? And that's what I'm going to take you. To understand how Monaco works with languages, Monaco is kind of agnostic to the language, in fact. Monaco is just, I'm a text editor, I'm just going to make great color stuff, but for everything I need, I'm going to rely on something called a language worker. And the language worker is really a fancy word to encapsulate something called the language server protocol. And if you look at, there is a specs out there called Language Server Protocol, and if you search a little bit for this, why Language Server Protocol was invented is there is so many editors out there, you know, Vim, VS Code, you have Atom, you have different kind of IDE. Well, they decided to all talk to each other and say enough is enough. We need to kind of unify all this way of working with these languages. We don't want to reinvent every time a new way to talk to each different editor. So they decided to work together and define this protocol called Language Server Protocol. That means if I write a Language Server Protocol for Monaco, I can also plug this Language Server Protocol if I wanted inside Atom or inside Vim or other IDE. So that's the principle. You have Monaco. Monaco says, okay, register your language server with me. Tell me which language this language server is backing. And tell me what services you are offering. So it's a kind of a la carte system. Not every language service server provide the same set of services. Here in the example we were going after, we wanted to address validation, suggestion, and formatting. In the future, we may add more like on hover or other kind of services. For us, we focused only on these three services for now. So Monaco, you register a language worker, and the Monaco, every time something happens on the script, it keeps sending that to that language server and says, know what? And it expects, you know, that language server to return, hey, here is the list of diagnostics, or here is the list of suggestion. And also reply to question like, I would like to format that string. In addition to this, the Monaco also, you can plug inside what we call a language syntax highlighters. It's for all the coloring, the theming, you know, the if looks blue and the parenthesis is green and all this stuff. This is all done through a language syntax highlighter. So let's continue and study. I'm taking you down the system right now. So, okay, great. So that's what I have to do, build a language server. How is it going to work with Arcade? So we receive this Arcade expression, it's a string, push that through this language server. Well, first things we need to do is this language server, we need to basically, first step to teach the language server is to teach what is Arcade. And one thing we have to teach is when we are going to face stuff in that string, that is the expression, certain things are, for us, called the global expression, the dollar feature, the dollar layer, the dollar map. That's all what we call the profile of your Arcade. It's like if you want today, you use JavaScript, you can use JavaScript in a profile called Node, or you can use JavaScript in a profile called Browser. They don't have the same function, and they don't have necessarily the same global, but it's JavaScript. The same for Arcade. Arcade can run for pop-up, or Arcade can run for dashboard formatting. Different profile, same language syntax if you want. So we can, first things we have to do is basically we teach our language server about what's the context you are supposed to execute. Now, how is the parser going about? Okay, that's nice. I have a script of string, basically, that represents the expression, what I have to do next. So what we have below this is called an Arcade parser. The Arcade parser is basically a system turning that string into a set of things we can understand and work with to validate and all this stuff. The parser is basically building an abstract syntax tree. It's basically a big JSON nested JSON with all the information. And I will do a small demo to show you what this is. Take your expression, give it to the Arcade parser, and the Arcade parser return to me an abstract syntax tree and a set of tokens. Let me switch to the demo. It's a little bit weird. Oops, I have to go there. Oops. All right, so what I did here is basically I placed, it's good, okay. So what I did here is I placed two code editors side by side. On one side, I have the code editor that I've tell this code editor, you understand Arcade, and I'm receiving back the AST, and on the right side, I use, again, another code editor, and I'm giving the JSON I receive. So you're going to see, as I'm typing, you're going to see the right side changing, and it's basically the parser just spilling out this abstract syntax tree. So if I type an expression like if, Fred, oops, equal great, just return, wow. Otherwise, return, boo. And you see the things changing on the side, right? So I type, and you see already certain things happening. There is some red showing up inside this editor, and you see basically as I type something happening on the right side. So what is an abstract syntax tree? I told you it's a big JSON. What it starts here, it says, yeah, you have a program, great. The program is made of a body, and this body has a collection of statements. So if I collapse this, a little bit here, you see that there is pretty much two statements. And that's pretty much right. I have one statement system here, and I have another statement system here. There is sub-statement after that, but from the root, you have only two statements. And that's what you're seeing here. So if I open the first statement, it says, what is this? Oh, it's an if statement. Oh, and it has a binary expression for the test. It's a binary of equal, equal. On the left side, there is an identifier. On the right side, there is also an identifier, etc. So you see that the parser has basically parsed this string, transform all of this into this abstract syntax tree. You can search on Wikipedia, Google, whatever. You can search AST, and you're going to find a lot of documentation about abstract syntax tree. At this point here, what I created is a nice syntax, no errors. Now, let me introduce one error. So if I just type dot here, boom. The parser is, I don't know what you're doing. It stopped, basically, at that point. It found this dot, and it doesn't know where to go after that, because it doesn't mean anything from an Arcade language. That doesn't mean anything. So it stopped, and it's an unexpected token error. But why do I get here these wiggly red things, and this stuff says something else? So we are going to talk about this. There is a difference between syntax error and logical language error. One, the dot is definitely a syntax error. You cannot have a dot at this moment. But these, the Fred and the is great here, are not defined. So it's good. The expression is correct. It's just that you cannot really do anything with this expression, but there is something that we don't know what to do with it. So difference, okay? Let me go back to my slide and resume. So before I go in details a little bit more about the syntax and everything, just one little note. Oops. Do I have to wait? No. Okay, we go. No. I'm going to replug. Okay, sorry about this. So one little things before I continue to the rest of the discussion about errors and all this stuff is that why Arcade is Arcade and why Arcade is not JavaScript less or TypeScript less. That was made a long time ago. Some people made decisions to actually more copy Arcade matching Excel expressions than JavaScript or TypeScript at that point. And the decision that was made is actually Arcade is case insensitive. So you can write return like this and it will work. That's one big issue we find. And the second one is that we did some decision like implicit return. So you don't even have to type return for the last sentence statement, sorry. It's an implicit return. And with this, we have a little issue because you can return an object, curly bracket, one, and in JavaScript or TypeScript, this is not an object, this is a label. So that's why we had to write our own parser, diverge. We are not really JavaScript. Don't try to think as arcade as JavaScript. Don't think this way, it's just arcade. It looks a lot like JavaScript, but it's not. All right, so if we continue with this, when we talk about any languages, you need to understand the way we think when an abstract syntax tree works is all in statement, expressions, and comments. That's all what you have. Everything you type is basically statements or expression or comments. And what we are also interested is by where this stuff were written in your code, so we want to know the location of all these things so we can highlight, turn things on and off. So let's go now a little bit deeper inside the system. So the parser, let's crack slightly open this parser and look at how it works. The parser is in fact based on the scanner. The scanner will just walk character by character, move, and then basically try to infer things. Oh, there is an I, great, it's an I. Oh, there is a if. If could be a statement, right? The beginning of the statement. So if there is an if and it's followed by a space, it's an if statement, probably, and then it keeps going like this, right? So it's basically inferring as it moves through characters. That's the scanner, it returns those tokens. And the parser tries to assemble this into statements or expression or comment. That's pretty much how the system works, and all of that, you store that into a JSON. That's called an abstract syntax tree. And of course, to do this, this parser, we have to teach the arcade language definition system, right? What we have if, we have when, we have for, we have this, etc. So that's the base. The parser is the base, right? You work with that, you receive an abstract syntax tree, or you can even directly work with the token from the scanner. So that's what I said before. The parser will stop at syntax error. Any syntax error, boom, that's it. So that's the first kind of errors you may get, and some of them we can not really guess what you did. That's the first problem. And we will look at that to actually get to the next level. We need to have another pass inside the abstract syntax tree to see if you have good syntax but illogical things. For that, we need to go back to, okay, what are the functions you are allowed to use and what are the input data you are supposed to have or receive when you are going to execute this expression. So that's the profile we feed to this validator. And what the goal of the validator is to return for Monaco something very precise called diagnostic. And diagnostic are either warning or errors. So here we see the validation pipe. It goes from the script given to the parser. Do we get syntax error? No, we are happy, we got an AST. Let's go try the validator, validate all of that, makes sense. In my case, you got the two red because Fred are variables that have never been defined, never, I don't say anything about Fred. It just use Fred and it says, I don't know what you're talking about. So these are logical error warnings that you will see. And those editor diagnostics is a very precise object that you have to return to Monaco, and Monaco does all the job for you, wiggling the red or the yellow and creating the box and showing the text and all the errors, the message you want to show. What is really the code on our side? So one thing you need to understand with this abstract syntax tree, so if you remember computer science, you have all this class about graphs. That's where you apply this, right? You traverse a graph, basically, right? It's a series of nodes, and you go in, and you walk down and back up, and you validate the next, and you keep going up and down inside that tree until you are satisfied with what you get. So it's called traversing. You traverse the abstract syntax tree. That's what if you ever want to look at the TypeScript parser or the JavaScript parser that exists out there, they will return to you an abstract syntax tree, and basically you walk the tree or you traverse the tree. That's the terminology used. In the example here, I'm on purpose creating something that the validator will complain. I created a function, foo, A, B, and I provided absolutely nobody to the function. So there is a lot of things going on and panicking here in the validator. First, you see that that's one of the validation we have. We validate function declaration, and you can see here that we have a block where we say, hey, if the block is empty, put a warning. But actually what happened above this is that A and B were declared as variable, as parameter of your function, but never used. So we are also complaining, saying, you have A and B, but you are not using them. So it keeps, whatever we find that is not really good, we kind of either error or warning out. So that's the validator. That's pretty much a job you do to create a validation for the whole system. And you see again here, that's the same, but I just explained that here it's the valid function, the invalid function below. And you see that on the right side, we got this abstract syntax tree, and you can see that pretty much on this abstract syntax tree, the body was empty for that. There is no body for that. In that case here, there is a body. The previous one, there is no body. All right, so that's cover. How do you go with a script, boom, parser, abstract syntax tree? Do we have warnings or errors? Now, let's say everything is working great here. The next things you want is as the user type. You want to say, you know what, you are starting to type FEA. You may want to use the function feature. So that's suggestion, right? So you see when you type, you see this box coming. It says, here's all the things that start with FEA. And that's called suggestions, or in the Monaco language, completion. So basically, same system will go, still the same stuff goes in. You pass the arcade, the script, it goes inside the scanner. And the difference here, instead of using the parser that may fail, because if you type dot, because you want to access a property of an object, the parser will panic, says, I don't know what you're doing, so it stops. Here we use the scanner, so we go up to the point where you type the dot, and that's where we will do the suggestion the same way. I'm going to accelerate a little bit. On the arcade suggestion that you see here, it's a lot of logic for the scanner. We say, okay, what the user type? Did he type a dot? Okay, so that's an object completion. If it's not a dot, that's probably going to try to provide variables, functions, and other things available at this point. So that's what you see here. You see I typed feature, and the suggestion basically provided all this list of things that starts with the word feature that are available in your language at that moment as function. Let's finish with the format. So the format is basically the opposite. You basically script, parse, you get an AST, and in fact, now what you are going to do is take this AST and rewrite a script. But now, because it's all object, I can put my indentation, breaking lines, do all sorts of things, and that's pretty much how I respill out now a reformatted string versus before if you had the long line on that things. The arcade formatter, it's really a system. We are quite opinionated. We like prettier. We say this is the way it should be formatted. You don't have too much to say about it. And the way it goes is it's a lot of back and forth. You go and you try, oh, okay, too long. Let's try to see if we can break somewhere, try again, etc. And eventually at one point we cannot do much. You are going to get your big lines. That's often happening if you have a long string or something like that. We cannot break that. So that's where we would stop during the formatting. That's an example here. You have your function, a bit, the line, the statement is too long on the line. The formatter will say, you know what, I can rearrange this. Here we go. And we break basically the function arguments here, and we place them on 2 lines. The second lines here, we are happy because it doesn't break the threshold. So we can keep it this way. If that second line was even too long, we would have done the same with the second line. Again, we format the second line, breaking, etc. So that's how you do for formatting. You basically read backward an AST back to a string. I'm running out of time, so I'm going to pass to Stefan. The demo for the formatting, I can do it maybe later after this session if some people are interested.
Or just do it live.
What?
Or just do it live.
Oh, yeah, I will do it after.
No. All right. Yeah, little switch of topic. I'm going to talk about the 3D rendering engine. So we stay true to the metaphor of under the hood here. No, joking. The real reason is I thought that's an interesting topic for you to understand how we build up a 3D rendering, what is all involved in there, and also to give you a bit of background and tools to write custom render nodes. So what are custom render nodes? This is something we just introduced. We announced it during the plenary. It's replacing the external renderer API, but it's also very simple, and I will show that to port existing code you may have in the external renderer API to render nodes. And it gives you way more flexibility. Two things there is that A, you can actually read the input data. So before with external render nodes, you had the frame buffer bound, and you could just render on top of it and add more things into it. Now you can actually read it and modify it or transform it, and I'm going to show a few examples of that. And you also have access to more information than before. Like in this code snippet here, you can get, for example, normal information. So at each pixel, you know in which direction the underlying face was facing. The way I'm going to do it is I will have very little text. I'll just go through it by pictures. We are going to look at this rendering here, which is like a moderately complex rendering. It doesn't have every feature we can do in it, but it has a lot of features in it. So who of you thinks there are more than 5 steps to render this frame? No one, or you're just shy, everyone? Who thinks there are more than 10 steps? Okay, 20? All right, let's see. You're all just shy, I can see that. And it's the last day. All right, so these are all the internal buffers we create when we render this frame. Don't worry about it, you don't need to understand this. We'll zoom into each and every single one of them, and I explain what's going on. So before we actually start rendering the actual 3D frame, there are a couple of pre-rendering steps we do. And the first thing is for all the features which have on-the-ground elevation modes, which we call internally draped features, we do render them in a, like you would render them in 2D, like in a 2D orthographic projection into a texture. And this texture looks like this. And later, that texture will be used to drape these things, for example, on top of the integrated mesh. So you see the buildings all colored here. These are colored by a polygon feature layer. And that's the draping texture we use then, which we drape on top of integrated mesh. The second thing is we compute the normals and the depth information, which you see here. Normals look very funny. Everything which faces in the same direction is the same color. And the depth is just shades of gray. The further down you go, the more black it gets. We then use that later on the next slide. And then we also, in this scene, we compute a shadow map. We use cascading shadow maps. You can Google this. This also means that this is relatively expensive in some cases. It really depends on what the angle of the sun is and what your viewing angle is. We need to render up to 4 times the scene. Here in that case, we have 2 shadow cascades for the frontmost stuff and then stuff behind. But if they really are in opposing angles, we need to render 4 of them to get a good precision on the shadow map. And then coming back to the normals and depth, the slides get scrambled there. We use these 2 information to do a pre-parse and compute a screen space ambient occlusion. So in computer graphics, ambient occlusion is this thing which happens when you have like a narrow alley. It gets very dark in there because light cannot go in easily. And screen space ambient occlusion is an approximation of that, and it computes this grayish looking shadow map. And you can see, for example, in this area here where it's very narrow, it gets dark. And then later, when we render the materials, this thing will get applied to the diffuse color of all the materials to make it darker. And now, finally, we can start rendering a 3D scene. So the first thing we do render is opaque color. So it's all the 3D geometry which doesn't have transparency. And that creates this type of buffer. You see here for reference in the background I put in the final image. It's still missing all the transparent stuff. So like this building, floor plates here. The water in that scene for some reason is transparent, and a lot of other things. We'll see when they come in. But to produce that one, we already use the pre-computed screen space ambient occlusion to make it gray in the places where we need to make it gray. The draped texture and the shadow map, because we also need to determine which parts of this are in the shadow, and then they get rendered darker. And this is already the first place where you can write your own custom rendering code. So you can actually get these 3 buffers you see here, and then render with WebGL your own geometry on top of that. This is replacing the old external renderer API. So when you did write an external renderer with a render function, this would happen at this place. And with that, I'm going to quickly switch over to our sample. This sample was an external renderer sample, and now for this release, we did port it to render nodes. There's also a section in the documentation which explains it to you, but it's really very simple. Things which are different is that you now subclass somewhere up here. Should have scrolled there earlier. No, that was too far. Whether, blah, blah, here. You subclass from the API class RenderNode. You create a subclass. This is JavaScript code. In the next example, I'll show you the TypeScript code, which is somewhat more readable. And then you declare what output you produce, in this case, Opaque Color. And of course, in order to do so, you also need to get Opaque Color as an input. And then all the other code is just OpenGL code, which was there in the external renderer sample already. And then in the render function, which gets called whenever we draw a new frame at the appropriate time, you want to reset the WebGL state to be at a well-defined point, bind the render target, which binds this frame buffer as the current frame buffer and returns as an output. Then do the same OpenGL rendering you did in your external renderer code, and then at the end just return the output, which is the same as the input in this case. And that's really all what is needed to port, with one exception. You had, in the external renderer API, you had a render context, which had a couple of helper functions like request render to request redraws, and also this.camera. And this is now all on the RenderNode class. Because we have a class and an instance, we can just pass that in. Now back to our rendering. So if you want to render opaque 3D geometry in a scene, you just plug in here and you draw your opaque 3D geometry as you did before. Then the next thing we are going to render on top of these opaque stuff is all the transparent 3D geometry. And there, since about 2 years, I would say, we did implement order-independent transparency. That's a technique which approximates the correct transparency, so it creates the correct alpha value. It does not, in all cases, create the correct color value, because if you have, it still doesn't order the geometry, it just renders it in the order you have it. And that's also why we do produce these free buffers, so we compute the opacity of it, the accumulated color, but then we do an additional pass to compute the frontmost color, so that we can guarantee that at least the frontmost transparent surface you have in your scene looks correct. If you then have multiple behind, they might not be in the correct order, but in reality that rarely matters, because most of the time you have the same color anyway, and then it's correct. Or even if ordering is slightly incorrect, since it's already behind something semi-transparent, it's often hard to see. Once we have this free buffers with transparent information, we composite this one on top of opaque geometry. And then additionally, as I very well drew here, we render the whole weather stuff. So this is clouds, atmospheric haze, and also the horizon colors, and then the precipitation, rain and snow, if you have configured that in weather. And at that point, you can, again, write your own render nodes if you want to render additional transparent geometry on top of that. For example, it's called transparent color, that input and output. This is a new functionality. I don't think we had that in the external renderer node. I'm not 100% sure because we had it internally, but I think it was never documented. So there, now you have a new place where you can actually also draw your transparent geometry on top of that. And then we are finally slowly getting to the end. There is a step called Composite Color, which then contains all the 3D content of the scene. So we do add edges to it. We do add the laser lines you have in the editing tools. So these are these little things which show you the same line of elevation in the scene, so you can have better Z precision when editing. And a couple of other things. It's very similar to the transparent color buffer, but it contains a few more things. Like if you look closely here on the floor plate building, you see the edges versus on the transparent color. Oh, you also see them. Okay, I took the wrong screenshot here, but they come in on top, trust me. And this is the last RenderNode endpoint we publicly released now for this release. And for that one, you have one additional input buffer, which is the highlight buffer. And the highlight buffer is currently binary information of what objects in the scene are highlighted. If you were in the previous session we wrote ahead, we mentioned that we will have multiple highlight colors, and for that we will slightly change then the semantics of that highlight buffer to help you identify what highlight is actually at this pixel. But right now, if you have a red color in there, it means this object is highlighted at this pixel. And if the red one also has a green component in it, it means it's highlighted, but it's actually hidden behind something else. And in that scene here, we have one of these floor plates highlighted, and you see that the frontal stuff is red. It comes across weird here. It looks a bit purple, but it's red. And then everything which is actually has something else rendered on top is yellow. I have one example for the composite color render node, and that's the plenary demo. So I'll quickly show you again how that looks like. So we had this scene here where we have a custom render node where we first enable a depth of field effect, which brings like this site nicely into focus. Then in the second step, I mask out the project site, and for that I'm actually using highlights. So I do highlight the polygon on the floor and the building, configure the scene view highlight options to be transparent, so the API doesn't render any highlight for me. But then in the render node, I have access to that highlight buffer, and I don't do then the depth of field where this happens. Then the next one is boosting saturation. This is really just a simple operation on the color buffer to boost saturation on the colors. And the last one is a bit more complicated. That's the spotlight shining down on the scene. So it's really a lighting calculation where I look at the normals, and everything which is facing up gets lit more, and you see that the building sides, which are completely perpendicular to the light, don't actually change the color, because there the normal is at a 90-degree angle to the light. And that's the effects which happen in here. And I'll now, do we have time? Yes, we do. I go in the code and go a little bit more into detail how that works. So this is the render node which you just saw in action. This time we are using TypeScript code. So we just subclass from our base render node. I actually have, I forgot about that. We have just a little helper class, because we ended up implementing a few render nodes. In the end, we only used one, but they all need to compile OpenGL programs, and we just centralized this common logic in this base render node. But then this base render node actually inherits from the API render node, which is part of the NPM JavaScript SDK package. And then this one, again, inherits from the base render node. And as I mentioned, for the lighting, I actually need normal information. So this is a required input to my render node. I need the color information, obviously. And then optionally, if there's anything highlighted in the scene, I'm also interested in the highlight buffer. And the semantics of this is really, if there's anything which I require, but for some reason the API doesn't produce, for example, if I put the highlights in here, but nothing is actually highlighted, then the render node doesn't get called, because it said I need this, and if that doesn't exist, well, then we don't call it. Versus for optional parameters, you always get called. They're just simply not then present here in the input array if they don't exist. And then I also produce a composite color output again. And then in my render function, I get all the input buffers I need. I'm going to look for my color input and a few other things, and set up my OpenGL state as I needed to. Most notably, I pass in, for example, the distance of the site to focus it correctly. This is just a variable to say which features of the render node are enabled. Like when I walked you through it in the beginning, we enable them one by one. In like a final application, you wouldn't need it. You would just have everything on by the beginning. Then the current time to do this pulsing of light. Also, the depth of field is faded in the beginning to not have a popping effect. And then the near and far plane, I need to compute the depth of field so that I know that where my focus is relative to the near and far of my camera. And the light direction is computing the light direction in view space, so I can do the right lighting calculation with my normal buffer. So this is taking the camera view matrix, rotating the camera center. So this is really a trick because our coordinate system, like 0 is in the middle of the Earth in render coordinates, and then it's a Cartesian coordinate system around that, which means that my camera center is always like the up vector at the Earth at that point. So that's why I'm rotating that one to get then a light shining down onto my scene. And then these are all the inputs to the shader I need. And then I'm just binding all these different inputs I requested as textures into the shader so I can read them in the shader later. So the color, the depth information, the highlights if I have them, and the normals. And then I do render, and the rendering, in the rendering, I'm really just rendering a screen space quad with my texture coordinates, the UV coordinates from 0 to 1. So the vertex shader is very simple. It just renders that quad. And then in the fragment shader, I kind of do like Photoshop style image processing. And let's start from the main here. I'm getting the input color because I'm going to need that in all cases. I'm sampling the highlight. What I'm doing here as a trick as well to have a smooth highlight outline is that I'm actually sampling the texture in the pixels around. So I'm sampling like a 3x3 grid of that one. And then I know that I'm either fully outside, fully inside, or in the area in between. I know how far away I'm from the border. So I get a floating point value between 0 and 1 back. And I can have a nice fading of a few pixels of that highlight. And that just looks much nicer. And then just ignore, let's say all features are on, so I'm gonna ignore like these feature flags because that's really just for demonstration purposes. So if I'm on the outside of the highlight, so that's my highlight border, I'm on the outside, I'm on the inside, I'm sorry, it's greater than 0.5, so I'm on the inside of it. That's the part where there is no depth of field, but I'm doing the luminance boost where that's just a mixing of the luminance with the color to boost that up. Then adding the spotlight, where I'm reading the normal from the texture, renormalizing that to be between -1 and 1. And then I have in the x, y, in the r, g, and b coordinates of that normal, I have my x, y, and z. And then the dot product of my light direction, which is shining down, that normal gives me the angle and the intensity of that light. And I'm just multiplying the color with that to make it brighter where the surfaces are horizontal. And then here in the end, I'm just mixing the strength in for the fading, and don't remember what this line does. It was an intense week. And then in the case, and then I return, but then in the case that I'm outside of it, I do the depth of field effect. And this is really the same thing as we have a sample for that one as well. Let's see if I can quickly find it. I didn't pre-open it. We have a bit of time, good. For the depth of field effect, we also have a RenderNode sample, which explains you that in detail. Color modification, custom RenderNode depth of field. So it's this one, where we are basically looking into the depth texture and depending how far we are from our focal plane and our aperture, are then sampling a bigger or larger area in the color buffer to create this blurriness effect if it's further away. And this is happening here. So first thing is that we get the linear depth for our current position, which is our depth in the scene. And then the distance between the focus point and that depth at the current position is our blur factor. And then in order to blur, we take 41 samples of the color texture of and the factor and with a more or less bigger radius, add these together, and then take the average of that, and that creates this blur effect. So if I move around here, you see that it stays at the same place. And the only thing we did differently in our sample application is that the focal plane was always tracking our project site by having a watch and the camera, and then computing the distance from the camera center to the polygon center to get the focal depth. I'm done, almost. And then there's really only one step afterwards. That's the final color, which adds the 2D elements onto the scene. So all the labels and icons, you can see them very small down here. And we also do a screen space anti-aliasing pass to get rid of the jagged edges along lines and sharp borders of objects. And that final color is then what you see on screen in the end. This is kind of, again, you don't have to understand it, but this is our internal documentation on how that render graph looks like. The orange boxes are the 3 custom render nodes I mentioned. And for example, here you see the one I just had last, the composite color that happens after all the post-processing, laser lines, and other things which we do. 2 more things you may want to be aware of. One feature we introduced, I think in 4.26, if I'm not mistaken, is adaptive rendering, which shows you the highest quality we can do when the camera is not moving. You may have noticed that things like water reflections, when you're moving, they are turned off because they would be too expensive to compute to have an interactive frame rate. But when the camera doesn't move, you don't care so much how long it takes, and then we fade them in and show them to you. So that means in idle, you always get very high quality, and when you're interacting or the scene is animating, we degrade a little bit to have a nice frame rate. And the things you get are things like screen space ambient occlusion, reflections, better atmospheric effects, better shadow quality, and things like this. And then orthogonal to that is the scene view quality mode, which forces some of these things to be on even in idle, in animating and interacting. And this is really for high-end devices. You can go to a higher quality and always have that thing, but then you're a bit on your own if it doesn't perform the way you want it to. 2 small notes if you want to write a custom render node. You have there raw WebGL2 access, so it's very easy to mess up something. If your matrices are wrong or your math is wrong, things get black or get funky. If you have developed WebGL code, you have experienced that. And internally, because we have all these frame buffer objects and these textures, we have a management system from that. So you can all the input textures you get, if you need to keep them longer, you can retain them. So we will not modify them and reuse them for something else. But be careful with that, because A, it's very easy to actually leak them, and then memory is gone very, very soon, because we render up to 60 frames per second, and these things are big. And also try to keep a lifetime, if you allocate your own, as short as possible, to we internally reuse them for other tasks if they have the same size and format. Internally, all the frame buffers we keep for 1 frame. And that's really, if we don't do that, we have to reallocate them every frame, and then you wouldn't get 60 Hertz rendering. But otherwise, we put them in a cache, and as soon as we see that we are out of memory, we start deleting them to not crash the browser tab. And that's all. And with that, please share your feedback if you think this was useful or not useful. We are always happy to hear from you. And we are open for questions.
Yeah, thank you. I hope we cheered you up well enough before the party, so you're all excited after this presentation. I don't know, we are ready for questions. Anyone? Yes, sir.
Does external renders go, the old external renders, I think this was in only almost every beta, does that go away?
Repeat the question.
It will go away, yes.
Repeat the question, sorry.
Yeah, sorry. So the question is if the external renderers will go away. Yes, we deprecated it with release, which means it's going to be gone in a year, earliest. But it's really, I mean, I did the porting of our existing samples and tests and stuff. It's really straightforward to port to render nodes. It takes you maybe half an hour, if that. It's really at the same point. The semantics are the same. It's just you can do more with it now.
Question? All right, thank you so much, guys. Have a great party. Thank you for coming. Thank you for listening.
And feel free to talk to us if you don't want to ask in front of everyone.